In mathematics, an identity is an equation which is always true, no matter what values the variables in the equation take. So, for example, the equation x squared minus y squared equals x plus y times x minus y is an identity, because no matter what value you put in for x and no matter what value you put in for y, we get a true statement out of this. Now, this is our standard difference of squares factorization. We don't always use the term identity to describe it, but it is, properly speaking, an identity. Much of the time, we are going to be interested in working with identities involving trigonometric functions. Now, part of that is because there are so many relationships in between the various 6 trigonometric functions that usually a given expression has many equivalent forms. And as we move further and start working on solving equations involving trigonometric functions, or looking even further ahead and start doing calculus involving trigonometric functions, it's often going to be very helpful to us to be able to rewrite an expression in a different form, an easier form for whatever task we're trying to do. And so, to practice that and to get into the habit of recognizing when we can simplify an expression, we are going to work with trigonometric identities and start verifying them. Now, verifying a trigonometric identity simply means proving that the two sides are equal. And there are lots of steps that we might take going through that process. We'll see a few of them in a second, but they're basically going to follow the same strategy. So to solve a trigonometric identity, or really I should say here, to prove a trigonometric identity, what we usually do is to start with the most complicated side, then simplify to get the other side of the identity. Occasionally, this strategy won't quite be enough, and occasionally we'll have to look at the first part and the last part and work both forwards and backwards, try to connect them up in the middle. We'll see that in a second. The facts that we're going to use, the technique, the mathematical tools we're going to use in order to accomplish this are going to be algebraic identities, such as the difference of squares formula that we have above, or just general algebraic knowledge about how we simplify complex fractions, for instance, using algebraic identities and basic trigonometric identities. Now, there are 2 kinds of basic trigonometric identities that we have seen so far that we're going to use, although we are going to see some other ones as we move forward in the course. The first are the reciprocal identities, and I group the tangent identities in with these ones. So the reciprocal identities tell us how the 6 trigonometric functions are related to their reciprocals. So we have that sine x is equal to 1 over cosecant x, cosine x is 1 over secant x, tangent of x is 1 over cotangent of x, cosecant of x is 1 over sine x, secant x is 1 over cosine x, and cotangent x equals 1 over tangent x. And this is for any x, including if x, the value that goes inside the function is an expression rather than just a single variable. We also have that tangent of x is equal to sine over cosine, and we have that cotangent of x is equal to cosine over sine. So these are 8 identities we work with. They are pretty simple ones. They allow us to take any expression and always express it in terms of sine and cosine. Although we can also express everything in terms of tangent and secant, or cotangent and cosecant, but we usually express things in terms of sine and cosine when we're going to use that strategy. We also have the Pythagorean identities. Now these are all based on first the original Pythagorean identity, which says that sine squared x plus cosine squared x equals 1. This we use a lot. We run into lots of situations where we have a sine squared and a cosine squared at the same time, and whenever we get that, we can have them equal 1. Notice also that we can rearrange these. So for instance, it's also true that sine squared is equal to 1 minus cosine squared, which we would get by subtracting cosine squared from both sides of this equation. We'll use that sometimes also. So this is the basic Pythagorean identity. Now, if we divide everything in the problem by cosine squared, we get the second Pythagorean identity, which says that tangent squared plus 1 is equal to secant squared. And now if we take the original Pythagorean identity and divide everything by sine squared, we get 1 plus cotangent squared is equal to cosecant squared. So we have these 3 Pythagorean identities. The first one is much more commonly used than the other 2, but the other 2 are very important. So we need all 3 of them. So these are the basic identities that we have that we want to use to try to verify trigonometric identities. So let's see some examples. Let's verify the trigonometric identity sine x plus cosine x cotangent x equals cosecant x. So this identity says that no matter what value of x you choose, no matter what angle you put into these trigonometric functions, if I take sine of x plus cosine of x times cotangent of x, that will give me cosecant of x. And you can see why knowing this sort of thing might be useful, because working with a single function, cosecant x, is going to be a lot simpler than working with a complicated expression like sine x plus cosine x times cotangent x. So let's do this. So we generally want to start with the most complicated side. In this case, we're going to start with the left-hand side, which I'll denote this way, LHS, the left-hand side. The book also uses just LS for left side. I prefer LHS, but that's just because that's what I'm used to. So we have sine x plus cosine x times cotangent x. And what we're going to do is we're going to create a series of equalities. We're going to say that this is equal to something, is equal to something, is equal to something, is equal to something, and eventually, hopefully, we'll be able to conclude that the whole expression is equal to cosecant x. So let's see how we do this, and for the first couple of examples here, I'll make sure and specify what kind of identity we're using as we go from one step to the next. This is not strictly necessary to verify an identity, but it is a good habit to get into to make sure that you are using the identities properly. So, first thing that I notice here is that I have three different trigonometric functions in my expression. I've got sine, I've got cosine, I've got cotangent. This is usually not very useful. Usually you want to be working with expressions that have exactly two trigonometric expressions, or trigonometric functions. Second of all, we don't necessarily want to pick any two because of the Pythagorean identities we worked with. We pretty much always, so I'll write, we usually want to use either sine and cosine or tangent and secant or cotangent and cosecant. So the first step in our problem, if our expression involves more than two different trigonometric functions, is to express everything in terms of one of these pairs of functions, either everything in terms of sine and cosine, or everything in terms of tangent and secant, or everything in terms of cotangent and cosecant. Often, expressing everything in terms of sine and cosine is easiest, and that's what we're going to do here. We have a sine and we have a cosine, but now we've got a cotangent, and so I'm going to replace cotangent x with cosine of x over sine of x using the cotangent identity. That cotangent is equal to cosine over sine. Okay, so let's see what that gives us. That'll give us sine x plus, now cosine times cosine over sine gives us cosine squared x over sine x. We're trying to prove that this whole thing equals just cosecant. In particular, we're trying to get down to just a single term, which means that we want to combine these two fractions. So sine x, I can multiply on top and bottom by sine to get sine squared x over sine x. Now my two fractions have the same denominator, so I can add them to get sine squared x plus cosine squared x over sine x. So these three steps in the middle, we're just using algebra, really. We're not using any sort of trigonometric identities or anything. And so now we will, though. We have sine x in the denominator, but now we have sine squared plus cosine squared. And pretty much whenever you see a sine squared plus cosine squared, you are probably going to want to replace that with 1. So this is the Pythagorean identity. And then 1 over sine x is in fact cosecant x. So this is the reciprocal, or a reciprocal identity. And now we're done. We have a string of equalities here. We have that the first expression is equal to the second, is equal to the third, and so forth and so forth and so forth and so on. And we finally simplified everything down to be cosecant x. And since equality is transitive, that is, if A equals B and B equals C, then A equals C, that means that the first expression that we started with is equal to the last expression, cosecant x, and we have verified the identity. And at a certain level, that's all there is to it. Now, these verifications can be complicated, and there are some tricks that we can often use. So let's look at some things that we might do here. So let's look at the next example. Let's verify cotangent theta minus tangent theta over sine theta plus cosine theta is equal to cosecant theta minus secant theta. Now, whenever you're copying this down, I am copying this from notes. You always want to make sure that you copy things down precisely. If you make a mistake, and if I wrote this as sine instead of secant at the very end, then I would have a bad time, because that equation is probably not an identity, and so I would not be able to prove it. So always make sure that you're copying your problems down, your equations down exactly correct, in order to avoid many minutes of confusion. All right, so we've got this. Now, in this case, both the left and right terms have some complexity to them. However, I would say that the left-hand side looks more complex to me than the right-hand side does. However, it is probably possible to do this problem starting with the right-hand side. It's just usually not as clear how to simplify things if you do. So we've got cotangent of theta minus tangent of theta over sine theta plus cosine of theta. Once again, we have a situation where we have more than two different functions involved here. We have cotangent, tangent, sine, and cosine. We want to turn this into expression involving either just sine and cosine, or just tangent and secant, or just cotangent and cosecant. Of those three options, changing everything to be in terms of sine and cosine looks simpler here, as it normally does. So let's do that. Cotangent of theta is equal to cosine theta over sine theta. Tangent is sine theta over cosine theta. And then the denominator is sine theta plus cosine theta. And that's just using the tangent identities. From here, we have a couple of options, but the best one is really something that comes from, comes from algebra. When we have a big expression like this that involves fractions, complex fractions, fractions within fractions, usually the best thing to do, the simplest thing to do, is to multiply the top and bottom of the big fraction by the least common denominator of all of the small fractions involved. So, in this case, the small fractions inside have denominators of sine theta and cosine theta. So, let's multiply the top and bottom of this expression by sine theta, cosine theta, and see what we get. So we need to distribute. So we get cosine theta over sine theta times sine theta cosine theta minus sine theta over cosine theta times sine theta cosine theta all over sine theta plus cosine theta times sine theta cosine theta. Another thing we know from algebra is typically it's easier to work with problems here if you leave the denominator in its factored form. So we're not going to distribute the denominator. We are, however, going to cancel the appropriate factors in the numerator. And so we'll be left with cosine squared theta minus sine squared theta over the denominator, sine theta plus cosine theta times sine theta cosine theta. Now, cosine squared theta minus sine squared theta is not something we can simplify using one of the Pythagorean identities. If that were a plus in between, if it were cosine squared plus sine squared, we could just replace it with 1. But it's a difference, and the Pythagorean identity doesn't help us with that. What does help us, though, is algebra again. So we can take cosine squared minus sine squared and factor it, because that's a difference of squares, and get cosine theta minus sine theta times cosine theta plus sine theta all over sine theta plus cosine theta times sine theta cosine theta. And now we can notice that we have this cosine theta plus sine theta factor that appears in both the numerator and denominator, so we can cancel those. So we're left with cosine theta minus sine theta over sine theta cosine theta. Now, at this point, we could try working backwards on the cosecant theta minus secant theta and see, well, it's not totally obvious how to get from this expression, the cosine theta minus sine theta, to cosecant minus secant. So let's put the cosecant theta minus secant theta down at the bottom and start working up from that. From our first line, starting with the left-hand side, we got expressions involving just sine and cosine. So let's express our right-hand side in terms of sine and cosine. This would be 1 over sine theta minus 1 over cosine theta. And so we're trying to find a way to basically stitch these two lines of reasoning together. We're trying to find a way to get the same expression coming both down from the left-hand side and up from the right-hand side. And we can see now, if we look at our term right here that we got from the left-hand side, that in order to make it look like the expression we have down below, we're going to need to split it up into two separate fractions. And we can do that. We can split up along the numerator. Write this as cosine over sine times cosine of theta minus sine of theta over sine of theta times cosine of theta. And now we see that we get what we want, because now we're going to have cosines canceling in the first place, sines canceling in the second. And now we can read this whole line of equalities from the beginning to the end, and they all work. They are all using valid logic and using correct Pythagorean identities. In this case, the only ones we used were the reciprocal identities, and using some algebra. Let's look at another one. Let's look at cosine of beta over 1 minus sine beta, and that's supposed to equal secant of beta plus tangent of beta. So another trick that we can use is the following. Let's start with the left-hand side again. And let's say we've got cosine beta over 1 minus sine beta. There's one thing we can do when our expressions down on the bottom, especially in the denominator here, are of the form 1 minus a trig function, or a trig function minus 1. And that's to multiply by the conjugate. So one tool that you have to work with that you can always try is to multiply by the conjugate. Now, the conjugate of an expression is that same expression, but with the middle operation switched. So, in this case, I will multiply the numerator and denominator by 1 plus sine of beta. And let's see why that helps us. We're going to get cosine of beta times 1 plus sine of beta over 1 minus sine beta times 1 plus sine beta. Well, let's expand out the denominator. Last time I said expanding out the denominator wasn't going to be helpful. This time it is. So if we FOIL this out, then we get 1 plus sine beta minus sine beta minus sine squared beta. Now, of course, the sine beta and minus sine beta in the denominator cancel, so we're left with 1 minus sine squared beta. All right, so then the question is, why is that helpful? Well, 1 minus sine squared beta is something that we can express. The Pythagorean identity says that sine squared beta plus cosine squared beta equals 1. Now, if we rearrange that, if we move the sine squared to the other side of the equation, this means that cosine squared beta is equal to 1 minus sine squared beta. So, when we have a 1 minus sine squared beta in the denominator, we can replace that with a cosine squared beta, which is good for us. Generally, simplifying the denominators of your fractions is an important step in terms of verifying an identity. Multiplying by the conjugate when you have an expression like 1 plus or minus a trig function will often give you something that you can use a Pythagorean identity to simplify. It's a very important tool, not immediately obvious when looking at it, but the existence of our Pythagorean identities mean that it's very important to keep in mind. So from here, we can cancel cosines. We have a single cosine in the numerator, and which cancels with one of the cosines in the denominator. So we're left with 1 plus sine beta over cosine beta. Now, at this point, we can look up again at our right-hand side. We see that we're going for secant of beta plus tangent of beta. We can see that we're trying to get an expression involving two terms, not just a single fraction, but two of them, so we can try splitting up the fraction like we did before. 1 over cosine beta plus 1 plus sine beta over cosine beta, which in fact is exactly secant beta plus tangent beta. And so we have verified the identity. Now, one thing that I want to mention is that working with these identities can often be a little bit frustrating. Especially when you're first starting out, you might be looking at an expression and think, I don't know what thing to use. I've got all sorts of things that I might use, but I don't know which one. Verifying identities usually involves a lot of trial and error. You may try many different strategies for proving an identity before you land on one that works. So don't feel bad if the first thing that you try to verify an identity doesn't work. Keep trying. Again, this is really an exercise in perseverance much of the time. So try not to get discouraged. If you need to try 3 or 4 or 10 different times using 10 different methods to solve an identity, then that's what you need to do. It takes a lot of practice and a lot of experience to be able to look at an identity and be pretty confident in the method to use to solve it. However, no one will be able to get every verification exactly right their first time. So get in the habit of trying and trying again when when your first attempt doesn't succeed. That's part of the process. It's normal. All right, let's look at showing that something is not an identity. To show that an equation is not an identity, we simply need to find one value of the variable which makes the equation false. Being an identity is a very, very strong condition. For an equation to be an identity, it must be true all the time, no matter what the values of the variables are. So, to show that something's not an identity, you simply have to find one value of the variable that makes the equation not true. So, for example, let's show that cosine x equals the square root of 1 minus sine squared x is not an identity. So if you tried to solve for cosine in terms of sine using the Pythagorean identity, you might wind up with something like this. However, if you did that, you would have a plus or minus in front of the square root. In this case, we don't. Cosine x equals the square root of 1 minus sine squared x is the equation that we're looking at, and we want to show that this is not an identity. So our thought process for this problem can go like this. Our thought process could be, well, the square root of anything is always greater than or equal to 0. This is a very useful fact that we have. But cosine of x is sometimes negative, which should indicate to us mentally that, well, then the two sides of this equation can't always be the same. So to show that, what we can do is we can try using some x that makes cosine x negative. So for instance, we know that cosine of pi is equal to -1. So let's try x equals pi. If we take x equals pi, then cosine of x is cosine of pi, which is -1. But the square root of 1 minus sine squared x will be the square root of 1 minus sine squared pi, which is the square root of 1 minus... Now, sine of pi is 0, so we get the square root of 1, which is 1. So in particular, this shows us that the two expressions that we've got, in this case, are not equal. And therefore, this equation that we had is not an identity. It's only true some of the time, not all of the time. Let's see another example. So let's look at sine squared x. I'm sorry, I wanted sine cubed x. We want sine cubed x minus cosine cubed x equals equals sine x minus cosine x. Now, the reason why we might come up with this is because it turns out that in fact, sine fourth x minus cosine to the fourth x, it turns out this is equal to sine squared x minus cosine squared x. It turns out this is true. This is an identity, and you should have this in your homework. And so we might ask, well, okay, what if we just change the numbers? What if we drop all the powers here by 1? What if we look for sine cubed x minus cosine cubed x? Does that equal sine x minus cosine x? And for this one, we might have some trouble determining this, because in fact, if we try a few common values of x, we do get a true statement. So for instance, if x is equal to 0, then we get 0 cubed minus 1 cubed equals 0 minus 1. That's true. And if x is equal to pi over 2, then we'd get 1 cubed minus 0 cubed equals 1 minus 0. That's true. And if x is equal to pi, then we get 0 cubed minus negative 1 cubed equals 1 minus negative 1. That's also true, because both sides are just equal to 1. And so forth and so on. We can try a lot of different angles and get equality here. However, that's not enough to prove that we have an identity. So let's suppose that the problem said, verify or disprove the identity. That is, it wants us to either show that this equation is an identity or show that it's not. And showing that it's not when obvious angles don't work starts the same way, actually. So one way that we can attack this is, let's just try to verify it. Let's try to verify this identity. We've got sine cubed x minus cosine cubed x equals. Now, here we're going to use another bit of algebra. We have the difference of cubes formula. A cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. So in our case, a is going to equal sine x, b is cosine x. So using that identity, we get that sine cubed minus cosine cubed is equal to sine x minus cosine x times sine squared x plus sine x cosine x plus cosine squared x. And so now we can simplify things further. We have this sine x minus cosine x term right here, which actually exactly matches the right-hand side of the equation that we were trying to work with. Now over here, notice that we've got a sine squared and a cosine squared, and whenever you've got a sine squared and a cosine squared added together, you can replace that with 1. And then we have plus sine x cosine x. So the question is, does this expression equal just sine x minus cosine x? Does this simplify down to just being the first factor? Well, the answer is no. This is not going to be sine x minus cosine x if 1 plus sine x cosine x doesn't equal 1. If 1 plus sine x cosine x doesn't equal 1, then this expression right here is not going to equal sine x minus cosine x. So that shows us that this is almost certainly not an identity, but to make absolutely clear about it, to make it 100% obvious, we should use a particular angle to prove this. Now we could, what we need is we need an angle where sine x times cosine x is not equal to 0. because we need 1 plus sine x cosine x to not be equal to 1. So we want to use some angle where the sine of that angle and cosine of that angle are not, where neither one of them is 0. Now, we could use a lot of our standard angles. We can use pi over 6, pi over 4, pi over 3, or 30, 60, 90 degrees. But we could also just construct a triangle. We know that the angles inside the triangle have sine and cosine values. So, to show that this is not the identity, or not an identity, we can do the following. We can construct a triangle with particular side lengths, and we can choose to take this triangle. So we could say, let x be the angle in the 3, 4, 5 triangle opposite the 3 side. So for this x value, it's not one of our normal measurements. It's not one of our normal angles. It's not 30, 60, or 45. It doesn't have a super nice expression, but we do know that it exists, and we know that sine of x is equal to 3/5, and we know that cosine of x is equal to 4/5. So that allows us to evaluate sine cubed minus cosine cubed of this angle and sine minus cosine of this angle. So sine of x is 3/5, and so sine cubed will be 3/5 cubed. Cosine cubed will be 4/5 cubed. So, working this out, this gives us 27 over 125 minus 64 over 125. So, 27 minus 64 will be negative 37 over 125. So that's what the left-hand side of this expression evaluates to at this angle x. On the other hand, sine x minus cosine x will be 3/5 minus 4/5, which is negative 1/5. And so we see that our two values are not the same. Negative 37 over 125 is not equal to negative 1 over 5. Therefore, these two expressions are not equal for this specific value of x, and therefore the equation is not an identity.